Hello everyone. In this video, we're going to start our study of circular motion and gravitation. So here's just a quick geometry review of some concepts that will be important during this lesson. So most important one being a circle. A circle is defined as the set of all points on a plane equidistant from the center. Important we say plane. If we say a set of all points, well, that could be a sphere as well. So you have to restrict it to a plane equidistant from a center. So this is our center O. So this is our center point. The radius is the distance from center to edge. So it's the distance from the center to any point on the circle, to the edge of the circle. So this R is the radius. And the circumference is the total outer distance of the circle. And it's like the perimeter of a circle. So if you were to take a piece of string and trace it in the form of a circle and then unwind it, the length would be equal to the circumference. Now, the circumference is given by this formula, should be very familiar. C equals 2 pi r, where C is the circumference, which we'll probably use meters. R is also radius in meters, and especially in physics. And pi, well, this is pi, 3.14159, and so on. So, yes, so this is our quick geometry review. So we'll get more into this, like these equations will be used a lot more in the next section. But it's good to get started with these equations. These are the angular rotational motion variables. So these are the angular motion variables, and these are three different variables which define rotational kinematics. So the kinematics of rotation and circular motion. These are angular displacement, angular velocity, and angular acceleration. So the equations, well, luckily for us, the equations are exactly the same, just with different symbols. So we use delta theta for angular displacement, which also means like the total angle traversed. And we use radians because radians are an actual number. Degrees are misleading, but radians are an actual number. 1 radian is equal to the angle, which on a circle, I'll just draw it out for you. So here's 1 radian, right? So 1 radian, right? It's a terribly drawn circle, but here's just to show the point. So if this was a circle, an actual good circle, for this angle of 1 radian, the length of the arc subtended, the length of the arc intercepted by this arc will be equal to the radius of the circle. So if the radius of the circle is r, and this length of the arc intercepted by the angle was also r, then this angle will be equal to 1 radian, which is equal to simple conversion, 180 over pi degrees. 180 over pi degrees. It's more like a math lesson, but it's important to know what a radian actually is. It's like a real number. That's what this is. So radian's like a real measure of an angle. It can be used in physics calculations. So 1 radian is approximately equal to 57.3 degrees. Because we can't actually use 57.3 in a calculation. It will get us false information. So that's basically what a radian is. I'll just leave this. Right? So let's move on. So here are just to show you how similar they are. So these are the angular equation, the rotational kinematics equations versus the normal kinematics equations. So you have this. Well, I didn't mention the rest of these equations. So delta theta equals theta 2 minus theta 1. This is in lowercase omega, so a little W looking thing. It's lowercase omega. Angular velocity equals delta theta over delta time, just like V equals delta x over delta time. And angular velocity is radians per second. So we have this, not an A, it's an alpha. So alpha equals delta omega over delta time, where alpha is the angular acceleration in radians per second squared, and delta t is our time. So if you look at these look exactly the same. The equations are exactly the same, just with different variables. With V replaced by omega, acceleration replaced by alpha. Well, t is the same in both cases. There's no angular time. There's no normal time and angular time. And delta x is replaced by delta theta. So these equations can only be used for constant angular acceleration, just like how the normal kinematics equations can only be used for constant acceleration. So it's important to note these. Now you might be wondering, how do you connect angular and linear values? Well, you use the radius. Specifically, the radius of the circle the point is traveling in. Right? If you have a circle, it's again a very poorly drawn circle, but this will do. So this is our center. It's your axis of rotation. We'll discuss about that more next time. So the center about which it's rotating, and this is like a little object, right? It's moving with angular velocity omega. Well, the actual velocity the coin is moving, because remember, the coin is moving. The velocity it's moving will be equal to the radius times omega, and delta x, the actual length of the arc is traveled through, is equal to the radius times the angular displacement. So in radians, that is traveled through. And if the object is undergoing angular acceleration, then the linear acceleration of the object is just the distance from the center times the angular acceleration. So r is like the distance from the center, or the radius of the circle the point is traveling in. Okay. So here's a quick practice problem. A disk with a radius of 0.2 meters is rotating at a constant angular velocity of 20 radians per second. What is the velocity of a single point at the edge of the wheel? Find the angular displacement of part A, what is the velocity of a single point at the edge of the wheel? Part B, find the angular displacement of the wheel after 11.5 seconds. And C, now the disk starts slowing down with a constant angular acceleration of 5.2 radians per second squared. How long will it take for the disk to stop? So you just plug into your equations, basically. So you have V equals R omega, then you substitute in values, 0.2 meters times 20 radians per second, and that will equal 4 meters per second. So then you could use the definition of angular velocity. Omega equals delta theta over delta time. You could solve for delta theta by multiplying both sides by delta time. And you get delta theta equals omega delta t equals 20 radians per second times 11.5 seconds equals 230 radians. And then we use our angular kinematics equations. The very first one, omega f equals omega naught plus alpha delta t. You solve for delta t by subtracting omega naught and dividing by alpha. So note that alpha is negative because it's slowing down. And yes, so 0 minus 20 radians per second over negative 5.2 radians per second squared, right? And that should equal 3.85 seconds. Okay, so here's a completely new concept. So we're going to start just an introduction to centripetal force and centripetal acceleration. So here's a thought experiment thought out by Newton. It's called Newton's cannon. So let's say you had this huge cannon, very powerful cannon, and you fired it from a tall mountain. You fired it at different speeds, right? As shown by these the green and blue. I used a different diagram before this, so ignore that. It's shown by these different lettered paths, right? So they'll land on different spots based on velocity, right? However, at just the right velocity, the cannonball will be too fast to land on Earth's surface, but also too slow to escape Earth's gravitational pull. So what does that mean? So you had your cannon, right? You fired it a bit. You fired it at a slow speed, and it just lands at point A, all right? Lands here. Now you fired it just a little faster, and it will land at point B. So gravity's bringing it down, from kinematics. Now C, it starts to get, it starts to gain some velocity, and gravity is not pulling it can't pull it that far down anymore. So we'll go to circle. Same with part D. Notice that it's basically in eternal free fall. It won't go down. Why? Because gravity's just not that strong enough to bring it down. It's just going too fast. So it will, by the time gravity tries to pull it down, it would have already gone here. And it would already have gone here. So it'll just keep on moving in a circle. However, if you shoot it too fast, if you overshoot the velocity, as in path E, he'll just escape Earth's gravitational pull completely, and he'll float off into space. However, in the instances of part C and D, and moreover in part D, it looks more like a circle. When gravity does keep the cannonball in orbit by having it go in a circle, it can be described as what is known as a centripetal force, and the ball is said to experience centripetal acceleration. So a little bit about centripetal acceleration. Centripetal acceleration is the acceleration an object feels when moving in uniform circular motion. An object can still have centripetal acceleration even if it has seemingly constant velocity. So imagine you have a little particle here, and it's moving with a uniform circular motion with a constant velocity. But you might wonder how it could even have acceleration. It's moving at a constant velocity. But look at it. The velocity is constantly changing direction, right? And velocity is a vector. It's defined by a direction as well as magnitude. So if the direction's changing, that means the velocity itself is changing. The speed is not changing, but the velocity is changing. So there must be a centripetal acceleration. So centripetal acceleration and centripetal force is always directed perpendicular to the velocity. It will point in or out of the circle it's traveling in. So since it's perpendicular to this velocity, the velocity will just keep on moving in a circle. The centripetal force is trying to grab it down, but the velocity is just too fast for it to actually bring toward the center of the circle. However, if the velocity becomes too slow, then the centripetal force will give out and it will just fall, and it will just stop moving in a circle. So here's our equation for centripetal acceleration. AC, and AC is measured in the same units as regular acceleration, meters per second squared, equals v squared over r, where v is the velocity in meters per second and r is the radius in meters. It should be say meters, not r. R is not a thing, so it's meters. So you can derive the centripetal force equation by using Newton's second law, just replacing acceleration with centripetal acceleration. If you do that, the resulting equation is this. So just do a quick derivation. So you have sigma F over M equals sigma FC equals AC. Right? Then you solve sigma FC equals MAC. And we learned from last time the formula for AC which is v squared over r. So you can just substitute v squared over r in there and you get mv squared over r. Over r. Okay, and keep in mind is the net centripetal force. We'll discuss what is positive and negative in the next slide. Okay, so here's how you solve these centripetal force problems. So keep in mind that centripetal force is not a new type of force. So think of it as like a type of label. So when you draw a free body diagram at a point, you don't use FC. FC is just a label. You don't use centripetal force. However, it's a label for one of the forces we already know. It's like tension, friction, gravity, and etc. Right? Provided that it is the force keeping the object moving in a circle, or is the force keeping like pointing away or into a circle. So let's say you have a ball on a string, okay? You're rotating it around, right? So when we plug in Fc equals mv squared over r, you have to make sure that Fc is a net centripetal force. I'll draw again. Right, so this is your ball. It's your ball on a string. All right, so it's rotating like this. This is velocity at this point. And then this is the ball at the very top. So is the ball at the very top. Sorry, it's not the actual top, but just live with it. So this is the ball over here. Okay, so when we use Fc equals mv squared over r, so we have a couple forces acting here. So assuming there's a vertical circle, horizontal circles are easy because there's only one force. Vertical circles is where the actual conceptual part of centripetal force comes in. So you know tension's pulling on the ball. Tension's always a pulling force. It'll try to pull the ball in toward the circle. So this is T, right? However, gravity will try to pull you away, pull you downward, out of the circle. It'll try to pull you downward. However, up here, tension will still pull you inward, right? Tension will still pull you inward, but gravity will also pull you inward. Why? Because gravity is always downward. Tension is just pulling in the direction of the actual like center of rotation, like where you're rotating the string, like from your finger, but gravity is always directed downward. So gravity will have an effect. So if you count all the forces going into or out of the circle, and only those forces. So if you're rotating on a table, right? If you're rotating on like a frictionless table, the normal force and the gravitational force encountered will not have a part in the actual equation. So keep in mind, for rotating it on a table, right, there's a free body diagram. Right? This is T. This is Fn, this is Fg. So Fn and Fg will not have anything to do with centripetal force. Why? Because it's not even going in the circle. Only tension's moving in a circle for a horizontal circle. Right? So this will be tension. Right? So it's not even moving it in a circle. So only the forces that move in or out of the circle. So if the force is going inward, it is positive, and if the force is outward, the force will be counted as negative, right? And if you actually do all the math, for an example like this, and you move a string and a ball at constant velocity, you'll see that the tension's greater at the bottom than it is on the top. Why? Because if you're moving at a constant velocity, gravity will try to oppose it. So in order to keep in uniform circular motion, you'll need a greater tension force. So it's why it's always a bit more difficult to move it up from the bottom of the circle if you're rotating a ball on a string in a vertical circle, it's always a bit more difficult because gravity's trying to oppose you. However, it's very easy at the top because there's not much of a tension force. Gravity's helping in providing a centripetal force, and since velocity is constant, centripetal force has to be constant. So tension will change. So tension will change depending on position. If the ball was here, say the ball was here, this is just a lot of conceptual stuff. It's so you can understand what centripetal force really is, what we mean when we say centripetal force. Gravity will be like this. Gravity will be mg over here. So it's not even facing in or out of the circle. It's like tangent to the circle. So we don't even count that. We don't count that. Tension will be pulling in toward the center. So T will just be mv squared over r. So no mg. So it'll just be mv squared over r. Okay, so I'll give you like a couple seconds to digest that. Then I'll go into some practice problems. Okay, so let's start analyzing some problems. So a coin is placed 30 centimeters away from a rotating turntable. The coin is moving at a constant 50 centimeters per second around in a circle. How long does it take for the coin to complete one revolution? Find the angular velocity of part A. How long does it take for a coin to complete one revolution? Part B, find the angular velocity of the turntable. And part C, if the coefficient of static friction is 0.6, what is the maximum angular velocity the turntable can spin at before the coin slips? Okay, so we have a free body diagram here. You have N or Fn, the normal force, and W equals mg, our force of gravity. So for part A, it's just simple application of V equals delta x or delta t, where delta x equals the circumference of the circle the coin is traveling in. So it's just basic substitution. You get 2 pi times 0.30 meters divided by 0.5 meters per second, and we get 3.77 seconds. Okay, so however, when we do, no, never mind. The next part is just as simple. So if you want to find the angular velocity of the turntable, use V equals r omega, solve for omega, where omega equals V over r, and then you use 0.5 meters per second to divide by 0.30 meters, which is 30 centimeters. Remember, all units must be in meters. You get 1.67 radians per second. So that's the angular velocity of the turntable moving at that moment. Okay? Now here's where the centripetal force part gets in. So Fc equals mv squared over r. But what exactly is Fc? Remember, we don't use, Fc is not an actual force. It's a label for a force. You might want to write Fc over here because centripetal force, but there is no such thing as friction and centripetal force, because the friction is the centripetal force. Keep that in mind. Friction is a centripetal force. Friction is the one keeping it on the turntable while it's rotating. So you can substitute in mu s mg. So mg is just equal to the normal force, and mu s Fn will be the maximum friction force before the coin slips. So mu s mg equals mv squared over r. You can cancel out m. So mu sg will be v squared over r, which if you are clever, you might notice, hey, that's centripetal acceleration. So you multiply by r and then take the square root. So square root of 0.6 times 0.30 meters times 9.81 meters per second squared. That will equal 1.33 meters per second. And so that's the maximum velocity the coin could take, but we're asked to find the maximum angular velocity the turntable can rotate at. So that is omega equals v over r. We just use our little simplification over here. So omega equals v over r, which is equal to 1.33 meters per second divided by 0.30 meters. And that equals 4.43 radians per second. So here's our second practice problem. A 2,000 kilogram car is attempting to travel through a road with a loop-to-loop with radius 20 meters. 20 meters. What is the minimum velocity the car must have at the top to negotiate the loop? And B, what is the minimum velocity the car must enter the loop with? All right. So let's try to analyze this problem. All right. So if the car is you just want the car to barely make it through over here, then the only centripetal force, just generally the only centripetal force, is the one contributed by gravity. So there shouldn't be a normal force. It's just very, very barely. So not much traction with the road at this bare minimum speed, but it will get you through the loop. So this is the absolute bare minimum velocity you need to go through. Otherwise, gravity will just pull you down and you'll slide back down the loop. So this is the absolute bare minimum velocity the car must have at the top to negotiate the loop. Right? So just to show you that. So you have Fc equals mv squared over r. You replace Fc with mg because gravity will be the centripetal force in this situation. You solve for m and you'll see, you could have also said the acceleration due to gravity would also be the centripetal acceleration if you look at this equation. So g equals v squared over r. You multiply both sides by r and you get square root of 20 meters times 9.81 meters per second squared. So which equals 14.01 meters per second. So you might think that if this is 14.01 meters per second, then this should also be 14.01 meters per second. But that is not right. Why? Because the car is going up. So this is where you have to incorporate past concepts like conservation of energy and the fact that the car is increasing height. So the car has to go at a faster velocity than before because it will go up in height. So some of its initial kinetic energy will have to go and turn into potential energy. So you have mv squared over 2 equals the mvf squared over 2 plus mgh. Now h will just equal the diameter of the loop. So the h over here will be the diameter, which is equal to twice the radius. And then I first already canceled out the ends. So that'll be v squared over 2 equals vf squared over 2 plus 2gr. So h is just 2r, so I just put in 2gr. Now what I would do, just to make it cleaner, I would multiply both sides by 2 to get rid of those fractions. V squared equals vf squared plus 4gr. Take the square root. You get square root of 14.01 meters per second squared plus 4 times 9.81 meters per second squared times 20 meters. And you get 31.3 meters per second. And in like car terms, that would be 112.8 kilometers per hour. So about 70 to 80 miles per hour. So that's pretty fast. That's faster than most like highway speed limits. That's pretty fast. But however, notice that the radius is 20 meters. So that's about like almost the size of a house. That's just the radius. So it's a huge loop. So this is the speed you will have to enter the loop with in order to successfully, this is a bare minimum speed you had to enter the loop with in order to successfully negotiate the loop. All right, so let's move on to universal gravitation. So Newton's most famous discovery was the fact that the force of gravity attracted objects together, that all objects have a gravitational pull, right? And this is known as Newton's law of universal gravitation. So in equation form is this: Fg equals gm1m2 over r squared, where m is the mass in kilograms of the two objects. F equals force, the force of gravity in newtons. R equals the distance between the centers of the objects in meters. And the proportionality constant G, that is known as the universal gravitational constant. It's known, this number is about equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. However, on the AP exam in some books, it will appear as meters cubed over kilograms seconds squared. So what I want you to take away from this is that the M doesn't have to be huge. M doesn't have to be like planets or asteroids. It could be ordinary objects. So like calculators and computers. However, if Newton said all objects have a gravitational pull, why isn't my calculator, which is on my desk, sliding towards me? Why isn't my book sliding at my face? Why isn't my computer sliding at my face? Because if you look and you actually do the math, M is just so like, FG will be so small because G is so small. G is equal to 0.0000000000667. So it's incredibly small. The force of gravity between you and another object is negligible. However, there is a force of gravity. There's a gravitational pull to all objects. However, it's most noticeable when you have a mass like Earth, which is about 6 times 10 to the 24th kilograms. So that's a huge gravitational pull. That's a huge mass. So when you have a huge mass like that, the force of gravity becomes noticeable. So that's why you can't like feel force of gravity in normal objects, and only the Earth is pulling on you, and you can only feel the Earth's gravity. So here's a practice problem. So Earth has a mass about 5.98 times 10 to the 24 kilograms. Find the gravitational force exerted on an asteroid with mass 4.37 times 10 to the 15 kilograms, a distance of 2 times 10 to the 10 meters away. And is this force greater than, equal to, or less than the force exerted by the asteroid on the Earth? All right, so you have Fg equals G m1 m2 over r squared. And if you substitute in all the numbers, 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 4.37 times 10 to the 15 over 2 times 10 to the 10 meters squared, that should equal 4.36 times 10 to the 9 newtons. All right? So that's 4.36 times 10 to the 9 newtons. So if we want to answer the conceptual part, this force greater than, equal to, or less than the force exerted by the asteroid on the Earth, well, this is just like plain Newton's third law. It will be the exact same. And even if you plug into the equation, let m1 be the asteroid and m2 be the Earth, because of like, what is it, the commutative property of multiplication, it will equal the same. So by Newton's third law, action-reaction forces, the force exerted on the asteroid by the Earth will equal the force exerted on the Earth by the asteroid. So that's just third law stuff right there. That brings us to another conclusion. So if the Earth is pulling on us, right? That means by Newton's third law, we are all pulling on the Earth. So when you're jumping up, while the Earth pulls you down, you also pull the Earth towards you. But why don't you notice? Well, because the mass of Earth is so incredibly huge. It's incredibly huge. So, like, the distance actually moved would be negligible, at least. It would be near zero. So you would never notice it. Even like a microscope or something, an electron microscope, you'd never notice the distance Earth moved because you jumped. So you are still pulling on the Earth. It's just that the Earth is so massive that the pull would be near zero. So here's another little application of the law of universal gravitation. So let's say the moon orbits Earth in a circular path where the radius 3.84 times 10 to the 8th meters. The mass of the moon is 7.35 times 10 to the 22nd kilograms. And the mass of the Earth is 5.88 times 10 to the 24th kilograms. Find the velocity at which the moon orbits around Earth. All right? So you could just see, notice that the force of gravity, we draw a little here. We draw a little here. We're focusing on the moon, so forget the Earth. I'm just drawing it for like third law purposes for the entire system. But on the moon, the centripetal force is Fg, right? That means and if it's moving in a circular orbit, you could just count gravity as a centripetal force, right? So you could easily find its orbit velocity like that. So in this example, Fg will equal Fc. Then you have G me mm over r squared equals mm v squared over r. And if you notice, cancel out. We don't even need the mass of the moon. We only need the mass of Earth. So you cancel out r's. You can cancel out one of the r's, take out the square from the left, and take out the entire r from the right. And then you get v squared equals gme over r, or v equals square root of gme over r. So that'll give you square root of 6.67 times 10 to the negative 11 meters cubed over kilogram second squared. Another way of writing it, times 5.98 times 10 to the 24 kilograms over 3.84 times 10 to the 8th meters. That should give us a velocity of 1,018.3 meters per second, right? So in this slideshow, we just learned about the rotational kinematic variables, and we also learned about centripetal force, centripetal acceleration, solving centripetal force problems involving uniform circular motion, and calculating the orbital velocity of the moon using summing up all of our concepts so far, except rotational kinematics. And yes, that is it. So just keep in mind, you're using physics that actual astronauts and NASA people might actually care about. So feel accomplished. This is a quite difficult topic to get around. So if you have any questions, please comment below. And see you next time for our next video. Thank you for watching.